Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Art. In this tutorial video, I'll go through this is 5129. This is a Cambridge International Combined Science Curriculum. Specifically on the chemistry side of it, this is a topic called metals. So metals and non-metals have different physical and different chemical properties. And in this particular table, we're going to compare a few properties of metals versus non-metals. So in terms of the melting point is the temperature. So it's the temperature for your solid to melt into liquid. So that means solid turning into liquid, and that happens at melting point. Metals in general have high melting point, whereas non-metals in general have low melting point. Now the other factor, the other aspect here is something called malleability. So malleability means you can hammer into thin sheets. That is a property of metals. So all metals are malleable. You can hammer metals into thin sheets, and that can be used to make, like, body of cars, body of aeroplanes, and so on and so forth. So metals are malleable, whereas we can say that non-metals are not malleable. So you can't really hammer non-metals into thin sheets. In terms of electrical conductivity, so whether you can conduct electricity or not, you are high electrical conductivity or you have good electrical conductivity, whereas non-metal have low electrical conductivity or poor electrical conductivity. Last but not least, we also have the type of oxide. This is whether you are acidic or basic or amphoteric oxide, as stated in the syllabus. It's part of oxide, acid, bases, and salts. So metal oxide, metal and oxygen combined together to give you metal oxides. So what we can say is metal oxides are basic oxide most of the time, okay? Whereas we can have non-metal oxides. Non-metal oxides generally are going to be acidic oxide. When they dissolve in water, they're going to give you acidic solution. Now part B, sodium is in group 1. As we know, group 1 has a special name. It's called the alkali or the alkali metals. Whereas we have group 7, chlorine is in group 7. That is what you call the halogens. Now describe the change in character of the elements across a period. Across meaning from left to right for only 1 mark. Really get straight to the point. We have metals, metallic elements or metals on the left side of the periodic table, and then we also have non-metals on the right side of the periodic table. So we can say that the metallic character decreases as you go across a period, or metals on the left, non-metals on the right. So that is how it changes, becoming less metallic across a period. So behaving less and less like metals across periods in the periodic table. Next up, we have reactivity of group 1 metals. This is from lithium to potassium. If you look at group 1 in the periodic table, they are not asking you lithium and potassium. They're asking you lithium to potassium. That means lithium to sodium to potassium. Straight from the last topic in the syllabus was periodic table. We cover a big chunk of group 1 alkali group metals. We also learned about the reactivity series, where we had heard about zil. So we know potassium is more reactive than sodium because of the zil reactivity series. So what we can say is, if potassium is more reactive than sodium, in turn sodium is going to be more reactive than lithium. So describe the reactivity trend. So reactivity is going to increase, and this increases down group 1 metals. Remember that when we did group 7 halogens, the reactivity decreases in an opposite sense. The next question, describe the trend in physical state. Physical state here refers to solid, liquid, or gases. And again, the question is asking you from fluorine to iodine. So in the periodic table, you have fluorine, chlorine, bromine, and iodine. These are the group 7 halogens. So VII is shown at the top of the periodic table. All of these will exist as diatomic F2, Cl2, Br2, and I2 because with 7 outer shell electrons, they don't have completely filled outer shell. So what I can say is F2 and CO2. So these two are at the bottom, indicates that there are two atoms that form covalent bonds. There is the meaning of diatomic molecule. Two atoms that are bonded covalently by sharing electrons to give you molecule. So F2 and CO2 are gases. Stated in the syllabus, CO2 is a pale green gas as an element, and then Br2 is a reddish brown liquid, whereas iodine is a gray-black solid. These are the appearance of the elements, whereas in aqueous solution, when dissolved in water, they have slightly different color. In this next question, we gotta pick each metal which could be used once, more than once, or not at all. First of all, reacts with oxygen, and you get this thing called amphoteric oxide. Amphoteric oxide means they can react with both acid and also bases. They can react with both acids and bases. In the syllabus, it's basically aluminium oxide as well as zinc oxide. Those two are the amphoteric oxide. So amphoteric oxide, zinc oxide, aluminium oxide, but which metal in the list is included here? Now reacts with oxygen, so you could have aluminium. We are looking at the metal, so you could have aluminium, or you could have you could have aluminium, or you could have zinc, whichever one you like. Okay, now used to galvanize steel. This is not in the combined science syllabus, not in the 5129 combined science syllabus, but if you really want to do this, the answer is really zinc, as zinc is more reactive than iron. Iron is present in the steel. The zinc will react instead of the iron, and they will protect the iron in the steel from getting oxidized or from reacting. Next one, the most difficult to extract from its ore. So that means it's the most reactive, because as soon as you get it, as soon as you think you have it, it's going to react because it's so reactive. So we know about the reactivity series. That is your poso-ka, Ma, there is your magnesium and aluminium. So there's your poso-ka-ma-zil. So zinc, iron, lead, and then hydrogen, copper, silver, gold. So hydrogen is not part of the poso-ka-ma-zil, but we know to add the hydrogen and then copper, silver, gold just below the hydrogen. The zil there is represented by Z, and then the I, and then the L there in the pronunciation for iron, and L for lead. So the most difficult one is going to be potassium. Straight from the series there, you got the potassium. So there's a very, very reactive metal. And then you have a group 1 metal that is less reactive than sodium. So where have we got sodium? Our sodium is here. So if this is more reactive than sodium, so we are not looking at potassium, we are looking at lithium, because group 1, the reactivity increases down group 1, lithium, sodium, potassium. So we can say that more reactive down group 1 metals. We want less reactive than sodium, so it's got to be lithium. Next up, last bit is protected from corrosion by oxide layer. That is just your aluminium. Stated in the syllabus, aluminium is protected by this aluminum oxide protective coating layer. In this question number 3, so we have 100 cm of air as part of environmental chemistry. As part of environmental chemistry of the air, we know that clean dry air have around 79% of nitrogen, and then we have around 21% of oxygen. We also know we have 1% of other gases, and these are all stated in the syllabus as well as the lecture tutorials on environmental chemistry of the air. This one is carbon dioxide as well as some noble gases. Not all the noble gases, but some noble gases such as helium, not helium, but neon as well as argon. Now state the name of the gas. Name, they want the name, not the formula. The most of the air is made out of this. This has got to be nitrogen. And as you pass air through this metal, which is copper, the copper is not going to react with the nitrogen. Neither will the copper react with the carbon dioxide or the noble gases, but the copper will react with the oxygen. So it is the oxygen that is being removed by the copper. And if I write an equation for it, you can imagine that it will be the copper plus the oxygen, and that will give you your copper oxide, specifically copper 2 oxide, or you can just call it copper oxide, at least in the combined science sense. Copper gains oxygen, so the copper is on the left, it gains oxygen, and you are forming copper oxide, which has oxygen on it. That is what you call oxidation. On the other hand, if this thing get oxidized, we can say that what happened to the oxygen? The oxygen is definitely getting reduced. So that is your reduction. Overall, you have a redox reaction. The reduction here is a technical term. It means loss of oxygen, whereas gain of oxygen atoms is oxidation. That's what happened to the copper. And as the copper removed the oxygen from the percentage of the A, coincidentally you have 100 cm cube. So 21% of 100 cm cube is 21 cm cube, because maximum percentage is out of 100% anyway. That is just simple primary school mathematics. Percentage is out of 100%. So when you have 100% of 100 cm cube, you have 21% of it. That means 21 cm cube is oxygen. So what I can say is, therefore, 21 cm cube oxygen. If you use up 21 cm cube oxygen, how much gas is left behind? Final volume left behind. So no more oxygen. So no more 21 cm cube oxygen. So you're going to get 100 minus 21. And that is the working, and you can press this on the calculator. You're going to get 79 cm cube, because you started with 100 cm cube, 21 cm cube oxygen. The difference of 79 cm cube is just the nitrogens and the other gases combined together. Oops, I beg your pardon, this is not 79, it should be 78. I was mistaken. Hence 78 plus 1 gives you 79% of the air remaining. There's 79 cm cube of air remaining without the oxygen that has been removed as a result of this redox reaction there. Question number 4, if you read the question carefully, copper is extracted from. So this is your product. Product will be on the right side of your equation, because we are forming that. So that's on the right side of the equation. Copper oxide is your reactant. So there is your starting materials. That is on the left side of the equation. Heating with carbon. So again, that is your reactant. And then you see here we are producing carbon dioxide gas. So carbon dioxide gas is our product. Again, that is on the right side. So if we complete everything into the word equation, complete the word equation, not chemical formula, we could see that by reading the English, by heating with carbons with the copper oxide. So copper oxide reacting with carbon, and then we are producing the copper, because we get the copper from this reaction of copper oxide and carbon. We get copper metal. We also get carbon dioxide gas. So we just write in copper metal as well as carbon dioxide, just reading the diagram and reading the question in English, to be honest. And we can comment a little bit about this, even though this is not being asked by the question, not at this stage. The copper oxide has got oxygen with the copper. Copper is just the metal without the oxygen. So I can say is the copper oxide loses oxygen. And when the copper oxide loses oxygen, this is oxidation. Oxidation involve, I beg your pardon, this is not oxidation. Loss of oxygen is reduction. Okay, reduction here, or reduce, we say copper oxide is being reduced, not in the sense of English, but in the sense of chemistry. The loss of oxygen is reduction. On the other hand, the carbon gains oxygen to become carbon dioxide. So if the carbon on the left hand side, it gains oxygen, gains of oxygen is what you call oxidation. So I can say that the carbon has been oxidized to form carbon dioxide. This is a redox reaction, because there is oxidation and there is reduction. There is the carbon gaining oxygen, oxidation. There is the copper oxide losing oxygen, that is reduction there. Next time, we're using words from the list, where we can use it once, more than once, or not at all. So copper oxide is a something, and it contains oppositely charged species. So we're looking at ions, because what we have is the copper, which is the metal ions, which is going to be cations, which is going to be positive ions. So cations are basically positive ions that come from the metals, And we get the oxide, which is basically the anions, which let me just draw using a different color ink. So the oxide is the non-metal ions, comes from the oxygen, group 6, and it would have gained 2 outer shell electrons. As it gained 2 electrons, it's going to have 2 negative charge there. So it is a compound. It is not an element because it contains 2 different elements, copper and oxygen. 2 different elements chemically combined together because you have positive ions and negative ions. What you get is an ionic compound, but you don't have a AN, you just have A. So in terms of English, you don't call it ionic compound here because this starts with A there. Now in carbon dioxide, as you know from year 9, dot and cross, carbon has 4 outer shell electrons, oxygen has 2 outer shell electrons, so each oxygen only share 2 out of 6 of its outer shell electrons, so I still have 4 more on each oxygen. This is as stated in the year 9 syllabus under covalent bonding topic, and therefore these atoms are chemically joined by covalent bonds. Covalent bonds involve sharing of electrons. If I draw out this thing here, this is 1 covalent bond, this is 2 covalent bond, this is 3 covalent bond, there are 4 covalent bond. So there are carbon forming 4 covalent bonds, and the oxygen sharing 2 electrons there, forming 2 covalent bonds for each oxygen. Sharing of electrons between non-metal and non-metals, what you call covalent bonding. So in carbon dioxide, each molecule contains 3 atoms because you have 1 and 2 oxygen atoms and 1 carbon atoms. So if the question say contains 2, then 2 elements, but 3 atoms. 2 different elements, carbon and oxygen, but 3 atoms altogether, 2 oxygen and 1 carbon there. Now this was the question where I earlier discussed, state whether to change from copper oxide to copper. So copper oxide to becoming copper. So what happened there? There is a loss of oxygen. This has got oxygen. This hasn't got oxygen. Loss of oxygen is reduction there. So is it oxidation or reduction there? Well, it is reduction. So what is reduction? Reduction is loss of oxygen. So I gotta explain it in the context of copper oxide. From copper oxide, so you start here, and then to this one, you end up that as a reactant. You end up with these copper as your product. So the copper oxide would have lost oxygen to form copper, and that is just what you call reduction, loss of oxygen there. So this next question, at high temperature, potassium can react with carbon dioxide, and that is because when you have the the zinc ion, and then lead. So this is the posocama, and then ZIL. The pronunciation with the I is actually referring to iron, but the symbol is Fe, and then the ZIL, the L there is lead, with the symbol being Pb. Just below lead you have hydrogen, and then below that you have copper, silver, and gold. So these are below hydrogen. These metals are not reactive with acid because they are below hydrogen. They are not reactive with acids which contain H plus ions. And to be honest, you don't really do this in your syllabus, but carbon lies somewhere in between aluminium and zinc. So reality here, when they say it can react, we can imagine that we can write an equation where we have potassium, which is more reactive than carbon, and that is why potassium can steal away the oxygen from the carbon. Potassium is above carbon, potassium is more reactive than carbon, can react, that's the hint, can react. So what happened then is the potassium steals away the oxygen, and you're going to get the compound formed between potassium and oxygen. You're going to call it potassium oxide. Quite straightforward there, I hope. And what happened then is what is left behind? What is left behind is the carbon dioxide having lost the oxygen bit, you'll be left with carbon. So name the white solid. So the potassium oxide must be the white solid because we know that carbon is black in color unless you are diamond. So that is basically the black solid that we use to pass water. If we want to treat water, we filter the river water, and then we pass it through carbon to remove all the bad taste and bad smell, and then the final step will be pass it through chlorine to kill germs and bacteria. So carbon is this black solid W here. We're gonna give it name. And then the white solid V is the potassium oxide, the potassium having stolen away the oxygen, and you're going to get potassium oxide. The spelling of potassium is in the periodic table. Oxide is just the O2 minus because the metals and the non-metals ionic compound. So during the reaction, what happened to the potassium and what happened to the carbon dioxide? We can think about this reaction in terms of what happened to the potassium first. Here, the potassium is a metal with no oxygen. Potassium oxide has an oxygen, so I can say that the potassium gains oxygen, and gaining of oxygen atom is what you call oxidation, gaining of oxygen. And therefore, the verb that you are trying to look for here is called the potassium gets oxidized with the ed as it gains oxygen. And what happened to the carbon dioxide is the carbon dioxide loses oxygen, so loss of oxygen, because carbon dioxide has oxygen, then carbon has no oxygen. Loss of oxygen is what you call reduction. So what happened to the carbon dioxide is that it gets reduced there. Part C, we want to separate the black solid. So solid means it does not dissolve. Insoluble does not dissolve. That is your black solid. And then you have solutions. Solution is basically the liquid. So that is soluble. That is insoluble. So the only technique that you can use is what you call filtration, where you filter off the insoluble and the soluble stuff. Of course, the setup is a lower secondary as well as a year 9 concept, where we use a filter funnel. So you must have a filter funnel, and then on the filter funnel I must put a filter paper. So there is filter paper, whereas the apparatus there is called the filter funnel. And then we need to label a few things as we collect the liquid. This liquid is what you call filtrate, and this label of the solid there, the solid that is left behind on the filter paper, is what you call residue. So residue is basically the solid that is left behind on the filter paper as you do filtration there. Part C, so we said that hydrogen is often included in the reactivity series, as we saw the polysulcamazil earlier, the polysulcamazil, and then hydrogen is there, and these metals below hydrogen is less reactive than hydrogen. They don't react with acid. All the metals above hydrogen in the reactivity series will react with acid, and they will give you these hydrogen gas. That is why hydrogen gas will produce a pop sound with burning splint. They don't tell you what gas it is, so you get 1 mark to identify what gas. And why in the world do you produce hydrogen gas in terms of idea of reactivity? When they say reactivity, that means the metal reactivity series as stated in the syllabus. This is zinc. The acid that we're using is called hydrochloric acid. Metal plus acid. So perhaps I can write that down first. Metal plus acid give me metal salt and also hydrogen gas. On the left side, you saw bubbles because there is reaction, whereas here on the right side, it tells you specifically no reaction. There is no need to mention there is no reaction again because the question already told you so. Repeating the question is really, really pointless and a big waste of time. So what I can say is zinc is above hydrogen in the reactivity series. In reactivity series, as stated in the syllabus, reactivity. I better spell that properly. Reactivity series. Therefore, zinc plus hydrochloric acid. You're supposed to know how to write the word equation. Hydrochloric acid gives you chloride. So it gives you zinc chloride as well as hydrogen gas. Like I said, how do we know there's hydrogen gas? Because we need to identify the gas. So the hydrogen gas burns with a pop sound. Give a pop sound. Burns with a pop sound. with lighted splint. Lighted splint is the one with the flame still going on, and that was what you put, the lighted or the burning splint. They mean the same thing. Lighted means still has got the flame, burning means still have got the fire, the flame, and it will burn with a pop sound as this reaction produces zinc chloride and the bubbles. You see bubbles, bubbles meaning gases. What you see is bubbles. You test for the gas with a burning splint, burns with a pop sound. The gas is hydrogen gas, and that's because you have metal. Reactive metal plus acid give you metal, salt, and hydrogen. Reactive metals with acid are all the metals above hydrogen, whereas this is silver. Silver is Ag in the periodic table. Ag is below hydrogen in the reactivity series. There is no reaction between silver and acid because silver is below hydrogen. Silver cannot displace hydrogen from H+. So I can write that point down. So silver is below hydrogen in the reactivity series. So silver is less reactive than hydrogen, whereas zinc is more reactive than hydrogen. Here silver is less reactive than hydrogen, and therefore no reaction with acid. No reaction with acid because here you will see no bubbles at all, as there's no reactions whatsoever, because silver is below hydrogen in the reactivity series. Silver cannot react with acid. Silver cannot kick out hydrogen gas H2 from H+ in the acid present. And that's it really overall for this work 1 for the combined science metals associated with this Cambridge International 5129 syllabus, but entirely suitable for any 14 to 16 years old students doing these combined science or coordinated science curriculum. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel, and do follow me at ptet.chemistry. That's at ptet.chemistry on Instagram, Facebook, Twitter, Telegram to get connected. Thank you for watching again. I'll see you in the next tutorial video.